Today we're going to learn about rational functions. Before we get started, I highly encourage you to be interactive with this video, be active in taking notes, stop the video at any time, and make sure you're writing down questions that you have that you would like to ask at a later time. So back to rational functions. In the word rational we see ratio. We should certainly be thinking about fractions. In particular, we should be thinking about x in the denominator. So we should always keep in mind with rational functions our home-based function, which is 1 over x. What does 1 over x look like? As a rough sketch, we should have this memorized from our lexicon. We should know that this function has a horizontal asymptote of y equals 0, a vertical asymptote of x equals 0. For this one, there's no x-intercepts, there's no y-intercepts, and the domain in particular is everything except x cannot equal 0 because we can't divide by 0. In the past, we've attempted to graph these functions based on transformations, and that's still something that we're going to keep in mind, but we're going to build off of that. So in our first example today, example 1, we're going to deal with a function that we'll call f of x, and f of x is 1 over x plus 2. Now 1 over x plus 2, we're going to be asked to graph this. We're going to be asked to talk about the domain, potentially the range. We're going to be asked to talk about our two asymptotes, vertical and horizontal. We're also going to be asked to talk about y and x intercepts. Related to horizontal asymptotes, we're going to have to discuss our limits as x approaches negative infinity of f of x, as well as our limit as x approaches positive infinity of f of x. While we can think about transformations and the fact that we have a horizontal shift here, left 2, an h value of left 2, we're also going to consider some other things. For example, a y-intercept. How do we always find a y-intercept? We set x to 0. And when we find f of 0, we'll get 1 over 0 plus 2, we'll get 1/2. And so this graph is going to cross the y-axis at 0, 1/2. For an x-intercept, we're going to set the y value to 0, and we're going to attempt to solve this. We'll get 0 equals 1 over x plus 2. When we multiply the x plus 2 over, we'll get 0 equals 1. And that's just never true. And as a result, we can say that we don't have any x-intercepts. In terms of the limits to the left and the right, if I were to plug in a very large positive number, I would then get 1 over that very large positive number plus 2. And the larger that positive number becomes, the closer and closer my limit will get to 0. And the same is true in a negative direction. If I plug in a very large negative number, add 2 to that, and divide into 1, the larger the number the closer we'll get to 0. Therefore, we have a horizontal asymptote of y equals 0. For a vertical asymptote, we're going to set the denominator equal to 0. X plus 2 can't equal 0, therefore x cannot equal negative 2. That's my vertical asymptote. And that's also my domain restriction. My domain is going to be all real numbers except x can equal negative 2. Now I'm going to piece these things together. In green, I have a vertical asymptote of x equals negative 2. In red, I have a y-intercept of 0, 1/2. And this is just roughly to scale. And then in blue, I know that my function is going to approach 0 to the left and 0 to the right. I'm going to piece these things together to get my final graph. And my final graph will look something roughly like this. When my function goes up on one side of a vertical asymptote, 99% of the time it's going to go down on the other side of a vertical asymptote. We'll discuss why that is later. From here, I could finish with the range. If I just look at my graph goes all the way low, negative infinity, to all the way high, except one value. We don't have a y value of 0, so this is going to be all real numbers, except y cannot equal 0. We're going to increase the level of difficulty on these pretty quickly here. In example 2, we're going to define a function h of x. H of x is going to be a rational function because x is going to be in the denominator. We're going to have x plus 1 divided by x squared minus 5x plus 6. And we're going to be asked to graph this without our calculator. We're going to be asked to determine what the domain, the range, the horizontal and vertical asymptotes. We're going to be asked to talk about the x and y intercepts, and then finally the limits as x approaches negative infinity, this time of h of x, and the limit as x approaches positive infinity, also of h of x. In addition, we're going to be asked to provide a rough sketch of this graph. There isn't a specific place where we would start. I personally would start at factoring my numerator and denominator wherever possible. My numerator doesn't factor, however my denominator does factor into x minus 3, x minus 2. I'll now graph the x and y intercepts. For an x-intercept, we set y to 0. When we set y to 0, we get x plus 1 divided by, it doesn't matter which form you use of the denominator, factored or unfactored, but by the time we multiply that over, that's going to go away, and we'll just simply be left with 0 equals x plus 1, so x equals negative 1 is my x-intercept. X-intercept negative 1, comma 0 for y. Y-intercept, we're going to set x to 0, and this process would hold true for any function. So the more complicated they get, make sure we're still holding on to our procedure. So we're going to find h of 0 here. That becomes 0 plus 1, 0 minus 0 plus 6. H of 0 is 1/6. So we get a point here for my y-intercept. I can plot those 2 points, roughly speaking, negative 1 in the x and 1/6 in the y. As for vertical asymptotes and domain restrictions, what we're going to look at here is the denominator. The denominator not equaling 0. Those are bad numbers for us. Here I would distinctly look at the factored form, and I would determine that x equals 2 and 3 are 2 locations where the denominator equals 0. Those are going to be my vertical asymptotes. My domain is all real numbers except x cannot equal 2 and 3. We're not dealing with holes today, but that's a conversation that'll come back in a second. We have 2 of these vertical asymptotes, 2 and 3. I'm going to roughly sketch these on. And then the final piece to my puzzle, before I can really connect the dots, is going to be my end behavior, or my limits to the left and to the right. For this function, again, I have a larger power in the denominator, and because the denominator has a greater power than the numerator, my graph is going to flatten out to y equals 0 on both sides. Therefore, the limit to the left of h of x is 0, and to the right is also 0. Therefore, I have a horizontal asymptote of y equals 0. So let's try to piece this together. We're going to connect this end arrow through the x-intercept, through the y-intercept, and then we have to go up from there. Because my graph is going to alternate sides, it's certainly going to go down on the other side of the vertical asymptote. I'm going to get some sort of U shape here that comes back down. I know that we can't cross through the x-axis because there is no x-intercept there. And then finally my graph is going to go to the other side of the vertical asymptote. Instead of going down, we're going to start up, and we're going to connect the end behavior on the right with that blue arrow. This is a rough sketch here. For this question, I could not determine the range without my calculator. So I'm going to just leave this as to be determined. I would need my calculator or some sort of calculus. I'm going to leave you with 3 problems to do and a couple of notes. In the future, some things that we need to pay attention to. What if the numerator does not have a lesser power than the denominator? What if the numerator and denominator have equal powers or equal degrees? How is that going to affect the end behavior? This is a conversation we've previously had, so I'd like you to keep that in mind. The second note that I would like you to pay attention to that we aren't discussing here is removable discontinuities, or holes. Where do we see removable discontinuities? How do we locate both the x and y values? These are otherwise known as holes. The questions that I'm going to leave you with today. The first question I'm going to leave you with, a of x, is going to be x plus 2, x squared minus 4x will be the denominator. I'm going to ask you to find the same graphic features and a rough sketch here, hopefully without your calculator. The second function, b of x, is x squared minus 4 divided by x squared minus 9. One thing to note here is that here the numerator and denominator are of equal degree. How will that impact the end behavior? And finally, c of x, and c of x is going to equal 4x minus 8 over x minus 3. Again, the degrees are equivalent. Tomorrow we might start playing around with the numerator having a greater degree, but for right now it's just the denominator of greater degree or the numerator and denominator having equal degree. Good luck with those 3 problems. Try them without your calculator. If you want to check with your calculator or Desmos, that would be a good resource.